Good morning, everyone. Today we are going to have a very exciting sessions on several outstanding lectures. Um, it's my pleasure to introduce Gil Bloch from NVIDIA. Gil is a software architect and his expertise is in interconnect, HPC interconnects, clouds, and in the past he has been working on FDMA technologies, sharp technologies, and many other exciting things. So, Gil, thanks to be here, and the stage and the audience is here.
Good morning. Hope you all had coffee. Hope you had good rest from yesterday. Hope you enjoy the session so far. My name is Gil. As Flavio said, I'm a software architect for NVIDIA, what used to be Mellanox Technologies. I've been with the company for more than 20 years, working on anything, any layer in the stack, starting from networking, topologies, transport definitions, RDMA, software systems. And today I'm going to try and squeeze everything into less than an hour. It will be challenging. Um, on some of the things, I'll just touch. Some I'll probably skip just because I don't have the time. Um, I have slides. I'm going to go through the slides, but if you have questions and you want me to provide more details on a specific topic, please stop me, ask for that. The target is not to get to the last slide, but you get as much information you would like to hear today. So we don't have to go through the slides, and feel free to stop me. If you have questions, I ask that uh, use the mic so it's recorded. Otherwise, I'll have to repeat. So just say me that, say that you have a questions. I'll give you the mic and we can use that so the recording will be complete. And with that, let's start. So the title of the talk is, the future of computing systems for artificial intelligence. And whenever we, as companies talk about the future, we need to use the disclaimer, right? Everything that I say about the future, I don't really know the future. Uh, okay, should work. So it comes with the disclaimer, and the disclaimer that I'm using, hope you're all familiar with Cassandra from mythology. Short story, she had the power to predict the future, but also she had the curse that no one believed her. So I'm not saying I have the power to predict the future. I'm asking you not to believe me. I'm asking you to ask the questions. If I say that this is going to happen in the future, it's my point of view. I represent myself. Don't really believe everything that I say. And with that, what I usually try to do is, not really to talk about the future. I will talk a bit about the future, but talk about the trends. I can see what happened in the past 20 years. I can see the acceleration of the rate that things are happening, so I can guess what's going to happen in the coming 2, 3. My company expect me to predict 5 years ahead. It's, predictions. Um, and before I start talking about technology, this is my computer. I brought my laptop here because that one was too heavy. Um, this is actually my old computer. It is now being, it's getting out of service. This is Selene. It's a GPU system that we use for research and development. We actually have a new one, EOS. This one was number 6, I believe, in the top 500 when it was installed. EOS, I believe, is now number 10 in the top 500. These are our internal systems that we use for AI. This is my future computer. This is how Midjourney envisioned my next computer. I told him, hey, I work for NVIDIA. NVIDIA, we use green as the color. It guessed that it needs to be green. It is going to be a smart running AI, basically doing some intelligence. So this is how it this is how I imagined my next computer. We will see. And now for the agenda, right? I'm actually going to talk about free technology. Um, I'm going to very quickly introduce distributed deep learning. I'm assuming most of you already know that. I'm assuming some of you don't. Don't worry about it. The idea is not to make you experts in distributed AI. The idea is to convince you that there are some requirements for data movements. We will, during this talk, focus on one, collective communication, all reduce. We'll do that quickly, just a few slides. Then I'm going to show you, as a part of the trends, the latest systems that we are building. I'm going to go from the chip level all the way to the system level, small system. Discuss the changes that we did from previous generations. Talking about trends, uh, I'll discuss the different things that we did, not all of them, obviously, again, we don't have enough time, and the reasoning behind some of the decisions that NVIDIA made when designing, it's not even future, it's the present systems that are already being shipped. Unfortunately, I cannot talk about next generation here. It's recorded, so I cannot. And then I'll focus a bit more on all reduce, discuss, how we implement that today, how in-network systems should implement that, and hope we'll have some time for questions. So deep learning, again, it's no one can squeeze all that information in 1 hour. So I decided to just give you the picture. Single GPU, you want to train a neural network. So you have your neural network, you have your training set. What you do is you read some of the training set, get it to your GPU, do forward path, right? You actually feed the data into the neural network, calculate the output, and based on the output, calculate the error compared to what you expect to get, do backward path, calculate gradients, update the neural network, and do that again and again. I hope it's not new to any of you. If it is, let me know. It's not that we can go back and go through the math of gradient descent, but I can put more details if needed. Now, the interesting part is that if we look at what's happening today with neural networks, it is kind of a consensus, at least today, that if you have more parameters, meaning if your neural networks has more parameters, more neurons, more connectivity, you get better accuracy. You get better result in whatever it is that you're trying to do with your neural network. Same for the data that you're using for the training. More data means more accurate results. And if you take the two, basically it goes to more compute, more more parameters in the calculation of the neural networks. More data, training data, end up with more compute. And there is actually, today you can see that everyone is trying to build larger systems. You can see that by just looking at the neural network size. This is focusing on neural networks for LLM, for language models. You can see that, starting in mid 2017 with transformers, it's been growing in logarithmic rate, about 15,000x the number of parameters in 5 years. If you try to compare that to Moore's law, obviously Moore's law, even if I'll ignore the debate if it's alive or not, it's not enough. right? Even if you do 2 times every 18 months, it will not sustain the rate of the requirements, what we expect from our compute systems to do. Bottom line, it means that we need stronger and stronger compute systems. And I call it compute systems. It's not that we need a compute engine. A compute engine will never sustain this rate. It's a compute system, and we will discuss this compute system today, that will somehow try to sustain this rate of growth in the compute requirements. And again, I try not to do that too much, but being NVIDIA, this is the new gold rush. Everyone is trying to dig the new gold, which is intelligence. We sell shovels. So going back to deep learning, we talked about, forward path, backward path. Obviously, one GPU, even if, we NVIDIA, we say, hey, we have the strongest, amazing GPU, it's not enough. So you need more than one GPU to be able to provide the compute power that is required for those models. So the first and easiest way to parallelize and distribute machine learning is basically data parallelism. How many of you are familiar with data parallelism? About 80, 90%, I guess. Okay, so very quickly, the idea here is that we actually duplicate the neural network, right? Have two copies of the neural network, put each copy on a different compute system and a different GPU in our case. What we do now is that we take the training data, and instead of feeding all the training data into a GPU, we split that into subset, into mini batches. And we feed the mini batches into the different GPUs. So now what happens is that each GPU, while it has the same neural network, it has less data to compute with, right? Because we split the data. So this is why it's called data parallelism. You have to do the forward path, you have to do the backward path, and now each GPU has its set of gradients, and you cannot update the neural network with that. What you have to do is basically calculate the average of the gradients. I'm not going to go through the math today. You'll have to believe me, it's easy to find papers describing. So doing that, now we actually need to calculate the average of the gradients, meaning we do a collective operation called all reduce. How many of you don't know what all reduce is? Don't be shy. Okay, at least one, which is great. At least one who is brave enough to say, I don't know what all reduce is. Basically, all reduce is an operation, right? We have distributed computing, we have multiple processes or multiple copies of this neural network. We calculate the gradients. We want to compute the average. The reduction operation is taking those vectors that reside on different computers and calculate some reduced data. In our case, it's average. It could be minimum, maximum, any operation. It's a reduction operation. So we get multiple vectors and we end up with one vector, which is some calculation on the set of vectors. And it's called all reduce because the result needs to go to all the members of this operation, right? All the members, each member contributes its vector and get back the result of the reduction operation. So it's all reduce, right? There are two parts to that. We'll focus on all reduce in this part. I'm going to convince you that all reduce is the most important operation for training deep neural network. Right after that, Salvo is going to say that I'm stupid and I don't know what I'm talking about. Always, the picture is complicated. For that hour, this will be our most important operation. So we need to do some reduction operation. It requires communication between the different compute engines. We will focus on that in most of my talk. After doing that, obviously we can update the neural network. So again, after this operation, all the compute engines has exactly the same copy of the updated neural network because we did all reduce. Everyone got the same result of the reduction operation. Everyone is updating a similar copy of the neural network. So you keep having equivalent similar copies of the neural network in each and every one of your compute engines. This is data parallelism. Just to sort of complete the picture, this is not the only technique. This is the technique we will focus on today, but there are other techniques like pipeline parallelism. In pipeline parallelism, you basically take the huge neural network that with the growing size of neural network, it doesn't even fit the memory of your compute engine, which means you need to split that. So we split that between multiple compute engines. Each one has some layers of the neural network. And now when you feed the data for that, basically it goes through the neural network. So you send the data to one GPU, it computes, the activation, it needs to send that to the next GPU, and you pipeline that, and there are all kind of issues in making that efficient, but eventually it works. It helps when you have very large neural networks, because now when it doesn't feed the memory of one GPU, you just split that and you can grow larger and larger. If you look at the communication pattern in this case, basically it's a point-to-point communication, right? Uh, the GPU that has the first layer is getting the data from whatever source of data you have. It's calculating the activations and send the result to the next layers, the next GPU. So it's point to point. Each GPU communicates with up to two other GPUs. The GPU with the pipe stages before and the GPU with the pipe stages right afterwards. So kind of easy, point to point communication. There are some optimizations where you actually hold different parts. A single GPU will not hold just a few layers in the pipe stages, but have a few layers of that pipe stage and a few layers of a later pipe stage. There are reasons for that. I'm not going to go in there. Again, there are interesting papers, very easy to find. If anyone wants more information, you can contact me or just Google. The last one and the easiest one to understand for most HPC people, because it's very interesting to see, AI people, um, they think they are smart. They try to reinvent the wheel again and again, and every once in a while they figure out, hey, people did that in HPC like 20 years, 30 years ago. But we already reinvented that. Let's give it a new name. An example would be, if you just need to multiply two large matrices, right? It's a distributed gem. That's what it is. But in the AI world, they call it tensor parallelism. You take two tensors, you need to multiply them. They're too large, they don't fit into a single GPU, or you just want to split a compute. All you have to do, like take B, split it into columns, distribute that into multiple GPUs. So each GPU has A and let's say one column of B. It does the multiplication of that and has one column of the result C. And now if you want all the GPUs to have all the results, you have to gather the different parts, right? And send it to all the GPUs. That operation is called all gather. I'm not going to focus on that, but again, this is just, we've done that many years ago. AI had to reinvent that. So the operation is all gather. That's the. Now looking into, again, I'm trying to show some trends here. Looking into how we train 1 trillion parameters neural network, right? It doesn't fit a single GPU. You cannot do that. I'm just going, to give you a very quick picture of how we do it. So we start with parallelism. Again, it doesn't fit into a single GPU. So we split that. We use distributed gems or tensor parallelism. This is one vector, right, on 8 GPUs. I'll go back to why 8 GPUs, but for now it's on 8 GPUs. What we do is we take the neural network and we pipeline it, right? Each pipe stage has tensor parallelism, but we have 6 pipe stages of that. So you can see how it scales the number of GPUs used. And then for each of those blocks, we do data parallelism because we don't want to feed all the data set into one. So you get this three-dimensional layout of your problem on the network, on your, sorry, on the system, right? This ends up with about 3,000 GPUs, a very small system. It depends on who you ask, right? But and this is probably the most common technique today. It's called 3D parallelism because it has the three dimensions. Data parallelism, pipeline parallelism, and tensor parallelism. It keeps growing. You know, people use expert parallelism. I'm not going to go into detail how that works. And different techniques. But the idea is that eventually we are looking into ways to take this huge problem and split it on a large number of GPUs. With that, I want to start talking about, okay, what does it mean for us? So there are all kinds of communication patterns. We talked about the point-to-point communication when you do pipeline parallelism. We talked about all reduced kind of operation, which involves, you know, a group of GPUs. Each one contributes a long vector of gradients. You know, their math, right? All reduced is actually doing reduction. We did not talk about tensor parallelism, but we can show that there are multiple cases. Sometimes it's an all-to-all communication, which is very heavy to the network. Usually tensor parallelism requires a lot of communication. It goes back to, I said that I'll say why we chose 8 GPUs to do tensor parallelism. The reason was that when you look at our GPU servers, usually it's a server with 8 GPUs connected with an internal connectivity called NVLink, because it's NVIDIA. You know, AMD has their own NVLink like bus. I'll give some more details about what it means, this bus. But it's usually about an order of magnitude faster than your fastest network that you have there. So it's extremely fast. It's local, right? There is the connectivity between those 8 GPUs with NVLink, but they are not connected with NVLink with the GPUs of the other server. So usually people will try to limit the tensor parallelism into a single server because of the data movement requirements. It's very expensive. Do that on your fastest network. If you have to scale beyond that, it's quite easy to show that your performance will drop. So the system topology, the system connectivity actually dictates how you run your distributed deep learning on your system. Here I'm trying to show, you know, generations and technologies compared in terms of bandwidth. So you can see that, you know, PCI. Do I need to explain what PCI is? No. Okay. Great. So, you know, if you look at PCI, it's, you know, Gen 4 is, you see the numbers. I don't remember them. I cannot read from that. So you see there is Gen 4, Gen 5, right? It's faster, still far from being good enough. This is why we came with NVLink connectivity. You know, before that, all the GPUs were connected with PCI. It was just too slow, so NVIDIA from the Volta generation started with NVLink, which is way faster. And then you can see that in Ampere and Hopper, it's just generations. Forget about the names, right? You shouldn't care about the names. You should see that we invest a lot of energy increasing the connectivity between GPUs using NVLink just because PCI could not sustain the bandwidth needed. Again, I'm going back to parallelism, right? Doing tensor parallelism requires a lot of throughput, a lot of data is going through the network. If you don't do that fast enough, you know, your efficiency drops and you pay a lot of money on a system that is working in low efficiency. It's not the best thing to do. That is inside, a box, right? You have PCI and you have NVLink, which should replace the PCI and give you higher bandwidth. But then you have those servers and you need to connect them. You do not connect them with NVLink. Again, I'll say a few words about it later, but you do not connect them with NVLink. NVLink doesn't really scale to thousands, tens of thousands, hundreds of thousands GPUs. That's not the case. Today, it's 8 GPUs. A few minutes later, it will be more, but still small number. So between, servers, you can use all kind of connectivity. This is showing, again, different generations. It can be Ethernet or InfiniBand. We push InfiniBand as we believe it's a better technology, better fitting for this specific traffic pattern. It's not better for everything. Basically, if you look at what's happening in compute systems, the world is going into specialized hardware. It used to be CPUs. CPUs can do everything. GPU is a specialized hardware. It's a programmable specialized hardware. It's not doing only a single task like it used to be 20 years ago, right? GPUs used to only implement the graphic pipeline. Today they are programmable, but still they're good at very specific tasks and extremely bad at all other tasks. If you try to run your storage software on GPU, it's just not going to work. So with that, I think that InfiniBand, and we started seeing Ethernet community understanding that standard Ethernet is not good enough. We need specialized network. So it can be InfiniBand, it can be the specialized Ethernet. There is a new consortium working on that called Ultra Ethernet. And again, we show here, if you look at the H100, it's the latest generation, till the next slide. We actually have 8 network adapters per server. It's actually 1 network adapter per GPU, providing 400 gigabit per second. So we keep growing with the bandwidths, and we invest a lot of effort and technology into increasing the bandwidths. I'll try to discuss shortly later, but it's not just the bandwidth or throughput, it's also the efficiency of how you use that, right? And I'll give one example, I have many. This is for point-to-point. It always translates to, hey, we don't care about point-to-point. I hope I try to convince you that all reduce is a very important operation. By the way, I'm giving the example of deep learning. It's just yet another distributed application, right? There are many other cases where in standard HPC, all reduce is important because you distribute your problem, you have local result on each one of your compute engine, and now you need to reduce this to a single global result. So while I talk about deep learning because it's easy for me as an example, it's just one application. So going to all reduce, there is a way to measure the bandwidths. And what I wanted to show here is that, hey, again, you can do that on TCP. Well, you can do that within the system on PCI, going all the way with NVLink. It keeps growing. And there is this NVLink for Sharp. And I promise you that before the end of this talk, you should know what Sharp is. Same for the network. Again, this is within the server, right? PCI and then NVLink. This is between servers. That's starting with TCP. Don't use TCP. That's the easy part. Growing with the bandwidths, with the new and latest network adapters, going all the way to 8 network adapters of 400 gigabit per second each. And I'll show a bit why I care about the fact that it's 8 per server and not 1 per GPU. It has some part, and again, with Sharp. With that, I actually, so until now, I hope I convinced you communication is important, data movement is important. I've been working for Intel 27 years ago. I know how to design an ALU that multiply 2 numbers. I still remember how to do that. It was many years ago. I was actually a hardware engineer. I'm not a computer science person, even though I'm a software architect today. Um, it's very easy to design an ALU that multiply two numbers. It's very hard to get the data, the two numbers into the ALU and the result back to where you want that. And I want to focus today on data movement and show you the new system. Okay, this is the Blackwell generation. We'll go through that twice. First, I will let you see that once, and then I'll do that with some explanations. Okay, so this is going to be my next computer. Okay. Let me, actually, I wanted to let it go all the way. I'm going to go through that again and discuss some of the things we've seen here. But this is 30,000, I think. It's, yeah, 32,000 GPU system. It's not a big system. You know, it depends on who you ask, but for those of you who follow Elon Musk, you know, that's easy because it's public. Whatever he's doing is talking about that and bragging about that. So it's easy for me. Um, he tweeted that he is going to build 100,000 GPU system this year, right? For XAI, by the way. He's going to build 100,000 GPU system this year and 300,000 GPU system next year. He said that. Okay. Yeah, we enjoy that. You know, it's good for me. It's good for NVIDIA, obviously, selling all those GPUs and building those systems. But, uh, you know, building a 300,000 GPU system that works is a challenge. And if anyone who's been with the HPC for a while, you probably know, you know, there are systems that the European Union will build or the DOE in the United States will build. And usually what they do is they start working on a system, they start a bid. It takes them anywhere between 3 and 5 years to actually deploy a new system. So we usually know about a system about 3 years ahead. You know, in 3 years, the DOE will build. I've been deeply involved in Summit. It was, I think, I don't remember if it was 2,500 or 4,000 GPUs. It was a big system for the DOE. we had 3 years to get prepared and make sure that we understand all the issues and solve that. With Elon Musk, he tweets that, hey, this year I'm going to build 100,000 GPU system. For you guys, just to understand, right? 100,000 GPU systems, this is quite a large system. 100,000 GPU system is 3 times that. You cannot put it in a single building. First, because of area, but more important, because of power. You cannot feed enough power to feed 100,000 GPUs into a single building. In most cases, you cannot have enough power to have 100,000 GPUs in one campus. There are all kind of limitations and regulations, and I'm not an expert in power distribution, but it's an issue, meaning that maybe 400,000, definitely for 300,000, it cannot be a single data center in a single location. It has to be co-located in different places, connected now with infrastructure, which is not a local area network, right? If you have multiple kilometers between the different parts. Latencies now are different if you communicate with your neighbor. We used to talk about topology. Hey, am I going through one switch hop or 2 switch hops? Now, who cares? Am I going through 100-meter cable or 10-kilometer cable? The amount of data that you can hold on a single 10-kilometer cable is huge. It's like a storage device, right? You just need to make sure you keep feeding it with data. It means that standard transport protocol just break. In a standard transport protocol, you have a window of data that you're allowed to send before you get an acknowledge, otherwise you stop sending. There are multiple reasons why you keep that. One of them is the state of the sender, right? You need to keep a state. It just doesn't fill a 10-kilometer cable. So everything breaks from transport through congestion control, through load balancing. I haven't even discussed what's going to happen when, a cable fail, right? 300,000 GPUs, meaning, it's probably 3 layer of switching, meaning I'm going to give, a rule of thumb. It's not really the number, but each layer is 300,000 cables. It's going to be optical cables because the distance is not short. And we're talking about high frequencies, high data rate. It's about almost in the ballpark of 1 million cables. 1 million optical cables, meaning 2 million optical modules. For those of you who had some experience with optical modules, they don't live forever. Optical cables fail every once in a while. If you have million of those, they fail all the time. They just keep failing and coming up. And maintaining that is a nightmare. And the network topology just keep changing because you keep losing parts of the network and keep bringing them up, and it's all dynamic. And that was only for the optical cables. What about the network adapters? What about the GPUs? Things will fail all the time. How do you keep an AI training job running for 3 months if something fail every few minutes? Resiliency or fault tolerance that HPC people got to was, hey, that's not so bad. Let's do checkpoint, right, every few hours. And if sometime, once a day or two it fails, we go back to the checkpoint. If something fails every few minutes, you don't even have time to do a checkpoint. You need a different solution, right? The number of questions that we have to ask ourselves, you have to ask yourself, right? We are doing the same, but we expect, the academy and the research people to also ask those questions. What does it mean, so I took the example of Elon Musk, and this is just this and next year. If you want to think few years ahead, what's going to happen if someone will want to connect 1 million GPUs? What are the problems that we did not have to deal with until now, but we will have to deal with in a year or two? There are so many questions, right? I'm not going to, I gave two examples, collocation, resiliency, and fault tolerance. There are others, and we will not have the time. I want to go through that video once again, at least parts of it, just to discuss some of the decisions that we at NVIDIA took when designing this kind of system. For some reason, at least for me, it will not go back. Let's try something different. Let's go now, hopefully. Okay, so this is the chip, right? We are a VLSI company. We produce the largest chip that the factories can manufacture. There are limitations because of the way we do those chips. Unfortunately, it's stuck. Okay. So this is one chip. It's not enough. We do two dies and put them in a single package. What you see as a single GPU, it's actually two silicon dies connected together. This is one, what you would call Blackwell GPU. So we package that and we put two of them. And that's an interesting one. This is where I wanted to start. So it's two GPUs, right? Connected through a very high bandwidth chip-to-chip connectivity. It's not PCI. It's not standard connectivity. It's a specialized connectivity to a CPU, right? This is the gray CPU that gives you extreme bandwidth that is at least 2 orders of magnitude faster than your PCI. So that those GPUs can collaborate and move data as fast as possible. They can collaborate with each other, and they have access to the CPU memory subsystem. Very fast access. It's not a PCI link. The main reason that NVIDIA did CPUs, you might ask yourself, right? We do GPUs, it's a great business. Why did you go and do CPUs? Intel are not making enough money to out of CPUs today. Why would NVIDIA go and compete in the CPU market where you have Intel and AMD and ARM and all those companies doing those? It doesn't really make sense. And the main reason is that no CPU company was willing to give us a CPU that provides us good enough access to the memory. Basically, if you look at this gray CPU, it's a nice CPU. I don't think it's the best CPU, but it's the only CPU that provides enough memory bandwidth. Intel, AMD, ARM, no one was willing to give us a CPU that allows the GPU to access the memory subsystem fast enough. GPUs has their own memory. They have an HBM, high bandwidth memory, that is a part of the chip with extremely high bandwidth access to the memory. But this memory is limited. You cannot put too much memory in there. And it's not enough. So, you can always put more memory in the subsystem, right? But then if the access to this memory is too slow, it's useless. It's being recorded. Anyway, for me, this CPU is basically an extremely fast memory controller. It has its own other tasks, but the first task is it's the fastest memory controller available today with chip-to-chip high bandwidth connectivity to the GPU. So it's all about accessing the data. Let me go through that. Too bad I cannot. So this is one board. We put two of them into a server. all kind of reasoning. But yeah. I don't remember. I think it was there. Let me check later. I don't, I don't remember any number. You can see by the color of my hair, I'm not young anymore, so I just can't remember numbers. But I'll find it later. Okay, I just don't want to stop now. It's public. It's not that we hide these numbers. Then we put networking, right? 800 gig per GPU. We have yet another DPU. Remember the DPU that we showed here? It's a device that Salvo will later give you some details on, so I'm going to skip. And now it's interesting part, and then Bloch says, okay, so we have 18 server trays in a rack. Till now, it's just a rack of servers. But now comes the interesting part. We talked about having NVLink connecting the 8 servers in today's DGX box. What we did here is we got NVLink out of the server, and we actually connect with NVLink the complete rack. What you will see here is actually an NVLink switch box that sits in the rack. We have multiple of those because of the extreme bandwidths, again, an order of magnitude higher than the network adapter data. So all of those GPUs now in a single rack are connected with NVLink fast connectivity. By the way, NVLink is not a network. Just a quick note, NVLink is a memory subsystem. The access to NVLink is a load store operation, just like a CPU would do to its memory. So all those GPUs are sharing the same memory domain. Meaning, if you talk about programming model, basically it's a shared memory system of 72 GPUs. And each, shared memory GPU is connected with InfiniBand. This is the quantum switch with 800 gig per GPU to the rest of those racks. So going back, right, I told you that, hey, tensor parallelism today is limited to 8 GPUs because if you go into the network, the performance is not good enough. You need very high bandwidths. The all-to-all communication pattern is extremely heavy. Now we moved from limiting that to 8 to 72 GPUs, meaning you have an extreme NVLink domain. It has its stores, right? If you lose one GPU on that, you might want to drop all the 72 GPUs. Otherwise, you start being asymmetric, and it's not easy to use. But once you use that, it gives you an extreme performance. I want to run through that. I'll actually skip. Again, trends. So we increase bandwidths in each and every layer, right? It's not just that we moved from 400 gigabit per second network adapter to 800 gigabit network adapter. This is just one detail. We increased the NVLink bandwidth. We increased the NVLink domain because we know that the large problems that we're going to need to solve in the coming years require extreme throughput on a larger groups of GPUs. We changed the connectivity between the GPU and the CPU from PCI to chip-to-chip NVLink. It's a chip-to-chip connectivity, extremely fast. We replaced the good old memory controller that CPUs had to a very capable and fast memory controller that now can be shared between, remember, one Grace, two GPUs, right? Two Blackwell GPUs, one CPU shared, and both CPUs have extreme bandwidths all the way to the CPU memory subsystem. So it's all about data movement. It's all about being able to get the data that you need into your ALU. ALU is easy to do. I can do that. And I want to quickly discuss. I'll take sort of 5 minutes, maybe 10 minutes of your time, sorry. I'll quickly discuss the collective communication. We talked about the system. I want to dive into collective communication. And as I said, we'll focus on all reduce. Hopefully you understand that all reduce is important. It's not the only important collective communication, but in the limited time that I have, I want to show you how we implement all reduce. The typical way is called ring algorithm. I assume that some of you are very familiar, some are not, so I'll give you a quick view of what we do. We split our vector. Let's say that we have 4 members in this all reduce operation, 4 GPUs. Each one has a vector, and we said that we want to calculate some reduction function. Let's say average, right? We want an average of those vectors in our output memory. So how we do that? We split the vector by 4. Each one chooses a single part of that, a different part, right? Load it to the GPU and move it to the neighboring GPU. Once we do that, now each GPU takes the next part and reduce it with the data that it already has because of the communication, and we circulate that. So if you look at that after n-1, 3 steps, each GPU now has a quarter of the vector, but this quarter went through all 4 GPUs, right? So it already has the reduced part. And now all we have to do is share that with the rest, right? And we do that again with rings. So you can put your part, and now you need to circulate that, send to the next one. Each one now has, it's a kind of a broadcast, right? Using ring. And after 2 times n-1, we actually have the reduced data in each one of the GPUs. This is the most common way to do all reduce with a small amount of compute engines. The main issue with this technique is that you can see that the number of steps is n, right? It's basically 2n steps, meaning the latency becomes an issue when you have a large number. There are other techniques for large numbers. I want to stay here for a second and say that, okay, so this is an extremely common technique. I want to show you that it's not perfect, but before I go there, we talked about Hopper, right? 8 GPUs, each GPU has its network adapter, but they are also connected with NVLink. So even there, when you try and figure out, okay, so how do I implement ring all reduce on, let's say that I have multiple of those, right? Not a single DGX, but few of them. And the interesting part is that this is a DGX, right? 8 GPUs connected with very fast NVLink. And remember, it's very fast NVLink. It's at least order of magnitude faster than the network connectivity, right? Each GPU has its own network adapter. This is actually kind of cheating because it's actually a drawing of the ampere, not Hopper, because there is a PCI switch here that connects 2 GPUs to 2 network adapters. It's not that way, but let's ignore the PCI switch for a second. Basically, what we can do here is have not just one ring on the network. Since the NVLink is fast enough, I can have multiple rings where NVLink sustain all of them. But each network adapter is a separate ring. And if I have multiple nodes, I just connect one ring and then another ring, and each ring takes a different part, but it's all reduced on the NVLink. And I can actually do 8 times faster, 8 rings working in parallel instead of one ring that goes through the entire network. I'm not going to go into details, just to show you that, hey, having different characteristics of different parts of your network, right? NVLink is a part of your, well, not network, but data transfer capabilities, means that you need to think of the algorithms, how you actually move data. right? If you want to do that efficiently, you don't have to, but if you want to do that efficiently, it's an hierarchical system that requires matching the algorithm to the system. What I wanted to say here, and this is the last part, I promised you that you will know what sharp is, so this is where I try to catch up with that. Till now we looked at the network and all it did was to move your data, which is nice, but it's not enough. We actually believe that there are other opportunities, and since we're in Italy, I've been using this example everywhere in the world, but in Italy I have to. It's the pizza way, right? Um, if you want to order a pizza, it's a well-known flow. You call the pizza place, you tell them what you want on your pizza. They'll put the dough, put the tomato sauce, put cheese, whatever you ask for to add on that, put it in the oven, and now you wait a few minutes, 7, 8 minutes, take it out, pack it, and send it to you, and now you again wait like 10 minutes. Depends on where you live and where the pizza place is. And my claim is that this flow is not good enough. And it's quite easy to understand that, with this great technology, I could actually, bake it when it's on the way and save time. And it works for pizza, it works for your data as well. And now we go to Sharp and show you how it works for your data. This is just one example, but this is the example for all the use. Let's say that you have multiple GPUs, right, connected through some network switches. This is a very simplified view of that. And now you will have to do all reduce. My claim is that if the switches will have some compute capabilities, it's very easy to do that. Okay, each GPU will send the data to the nearest switch. This is how networking works. Each switch will now calculate the average of the vectors coming into this specific switch. So this switch will calculate the average of the inputs from those, and you can see, and send the result up the tree. So basically, this switch now calculates the average of these inputs. Well, when I say average, whatever, the reduction operation, right? It can be sum, it can be minimum, maximum, whatever operation you want, you can do that. And now, if you look at the root of this tree, it actually has the reduced data. But it's a switch. Okay, that's not what I wanted. All it has to do is to send it down the tree again. And all you have to do is send the data once, receive the result once, and compared to the ring algorithm, it's actually effectively double the bandwidth, right? We don't have to send the data twice on the network. So it's an in-network technique that effectively doubles your bandwidth. And what changes here is not that we know how to do faster ALUs, or not that we did faster network adapters or faster optics. We just moved the problem to the right place. If you look at the interesting part is that the main problem of doing the compute on the compute engines, that you need to get the data into the compute engines. And compute engines have limited bandwidth. If you look at the network, networks scale with the bandwidth that you want, right? If you want to add more GPUs, you will just add more switches. And each switch now, those two switches in parallel compute the reduction operations. And if you need more switches, just add more switches. And the network switch is a machine that is designed to absorb high bandwidth from multiple sources. This is the difference, right? It's not that we have a different ALU technique or different, it just put the problem on the most fitting place in the system. Look at the system that you have, and it's not that everything should move here, right? I'm not saying let's do back propagation on switches. It doesn't make sense. I'm saying that some parts should move into the network just because it makes more sense. It changes the complexity of the solution because you do that in the right place. Quickly showing some numbers. I'm just comparing here. This is the time it takes to do all of this operation with different numbers of GPUs. Just comparing software to in-network, right? Software is the latest and greatest algorithm in our HPC software. Compared to doing that in the network, you see that when you increase the number of nodes, all software algorithms eventually have some relationship to n. They grow, the time it takes to do the operation grows with n. It can be logarithmic, it can be linear, but the in-network computing basically doesn't, because you just add more switches and you do that in parallel. I'm kind of lying when I say that it's not an order of one. You can see here that when moving from 8 to 16, it had a little step. The difference is that with up to 8, I was connected to a single switch. More than 8, I had 2 switches, but I needed another layer of switches. Another layer of switches adds latency. But if you look, so that's 2 layers with 3 layers factories of, the latest switches today with very high radix. You can connect up to 1 million GPUs. So, it's I can say that it's order of one, even though it's not. It's close enough.
Okay, so let's take Gil again.